For this chapter, we're going to be focusing exclusively on data analysis, and we're going to go into a little more depth about some of the types of data analysis we talked about more briefly earlier in the semester. Now, descriptive statistics describe what's happening in the data, kind of generally what's going on. Central tendency tells us about the average scores. However, what we're going to see is that central tendency isn't necessarily enough to describe all of the scores or describe everything that's happening. So let's say I'm doing a study and I'm interested in sleep habits depending on what time students take my class. What I've got here in this table is a frequency distribution. This hours of sleep is the possible scores. Frequency here tells me about how many students got each score. So I have 3 students who slept for 3 hours, or excuse me, I have 2 students who slept for 3 hours. Going down to the bottom, I've got 2 students who also slept for 9 hours. So based just on this table, what I can see is in my 9 o'clock class, the average student slept for 6.1 hours, which is my mean, and I had 29 students in the class. Now let's say I'm interested in comparing my 9 a.m. class with my 11 a.m. class. On the left, I've got the data for my 9 a.m. class, which you can see is the same from the last slide. On the right here, I've got the data for my 11 a.m. class. What you'll notice is that although, if we come down to the bottom, the means are exactly the same, the means for both classes are 6.1 hours. Both have the same number of students at 29, but you'll notice that the distributions for the 11 o'clock class looks very different than the other one. So just describing it based on central tendency doesn't really tell us all that's going on. The variance is another piece of information that can serve to describe what's happening. And the variance tells us about how spread out the scores are. The bigger the variance is, the more spread out the scores are. So what I have here is the frequency or the variance tables, so you can see the distributions in a little way, different way for the 9 o'clock class and the 11 o'clock class. What you can see is for the 9 o'clock class, although the mean is still exactly the same, the variability is different. For the 9 o'clock class, the range is from 3 to 9. For the 11 o'clock class, the range is from 0 to 13. So when we look at the mean and the variance together, it gives us a more complete picture of what's going on in the distribution. Okay, so the standard deviation is the most common measure of the variability. In general, what it does is it uses the mean as a reference point and determines whether the scores on average are close to the mean or far from the mean. When the scores on average are close to the mean, they'll have low variability. When they're far, they'll have the standard deviation measures how far on average scores are from the mean. This is the formula. Don't panic, you don't need to memorize it. And what we're going to be doing next is kind of walking through it. In general, the idea is we're going to look at a deviation, which is how far an individual score is from the mean. We're going to square that deviation, add all of the deviations together, and divide by the number of scores. So let's walk through and see how and why we do each. Okay, so the deviation, like I said, is the difference between each score and the mean. So this x minus m, and the x indicates each individual score. M is the mean for the whole sample. So what the deviation can tell us, the number will tell us how far a score is from the mean. So is it 2 points from the mean? Is it 10 points from the mean? The sign tells us the direction of the deviation. Is it higher than the mean or is it lower than the mean? Okay, so this is data from a hypothetical experiment. Each row in each column, number in the score column tells us an individual person's score. So we had 5 participants. And the first thing we need to do to get the deviation is to find the mean. So we can add up all the scores together and I get 20. I know there are 5 scores, which means that our mean for this sample is 4. And then to get the deviations, what I want to know is the difference between the individual score and the mean. So for example, for the person who scored 7, my deviation would be 7 minus the mean for the whole group, which is 4. This person's deviation is 3. I go down to the bottom. This person's score is 1, so 1 minus 4 is minus 3. You can see the number, it tells us how far away from the mean they are, and then the sign tells us the direction. This bottom person has a negative score, which means their score is below the mean. This person has a positive score, which means their score is above the mean. Okay, so when we define the standard deviation, we said the goal was to find the standard distance of the mean. So if we want to know the standard variation from the mean, we want a single number to represent kind of our whole sample. The obvious way to do this, the most logical way to do this would be to calculate the mean of the deviation scores, right? So we know everyone's distance. An easy way to talk about the average distance would be to get the mean. Slight problem with this. In order to get the mean of the deviations, we need to add them all up and divide by how many there are. However, when we go to add up the deviations, so we're adding down the deviation column, if you add them all up, you end up with 0. So the reason we have this problem, and so the reason this is a problem is because if we want to take the mean, we need to divide the sum by the number of scores. So 0, the mean would be 0 divided by 5. 0 divided by anything is always 0. So 0 is clearly not a good depiction of the average distance from the mean. However, we have this problem where with the negatives and the positives, we always end up with 0. The reason for this is because the mean is our balancing point of the deviation. Because of this, if you add all the deviations up, you're going to get a 0. So the mean is the point where scores are balanced in distance. Or, for example, it tells us about how much each individual would get if the total was divided equally among people. We can think of this as a seesaw, where these are all of our points. We had 3 points that were negative, 3 deviations that were negative, a 3, a 1, and a 1. So we had a total of 5 points below the mean, and then 2 people scored above the mean, got a 2 and a 3, which means 5 points above the mean. Because we're centering our deviations around the mean, they're always going to equal, the sum of them is always going to equal 0. So how do we get around it? How do we make it so that when you add all the distances from the mean, we don't get 0? So how do we make the negative values go away? Well, statisticians are pretty tricky, and they know that if you square any number, it always equals a positive number. So we get rid of those negatives if we square them. So what we're going to do is square each of the deviation scores and add them together. This is called the sum of squares. Instead of taking the average of the deviations, we're going to take the average of the sum of squares. Let me show you what this is. So here we have each person's score. We've got each person's deviations. We know if we add up these deviations, they're going to equal 0. So now what we're going to do is square each deviation. If we go through and calculate this, for example, for this person, they scored a 7. Their deviation score is 3. 3 squared equals 9. This person scored a 3. Their deviation is a -1. -1 squared equals 1. Now what we can do is add up all of the squared deviations, and we no longer get a negative number. So if we add up this column, the square deviation column, we end up with 24, and we can divide by the total number of people, which was 5, to get an average. This average is called the variance. So remember, the variance is the average of the squared deviation. We want everything to go back to our regular metric. So what we're going to do is, to get back to the same units, we're going to take the square root of the variance. We don't care about the average squared deviation. We want to know the average deviation, or the average distance. So taking the square root brings us back to our original back to our original scale, and gives us the average distance from the mean. And that is the standard deviation. Bigger scores or bigger standard deviations means that there's more variability in a set of scores, means that the average distance from the mean is farther. And just to show you what this looks like, again, we've got each person's score, each person's deviation. We square the deviation. We can take the average of the squared deviations, which gives us the variance. And then to get our standard deviation, we have to take the square root of the variance. So the standard deviation is 2.19. What this tells us is the mean, or the central measure of central tendency for this group of scores is 4. So the average person got a 4, but on the average distance from the mean was 2.19. So while the average person got a 4, many people scored within 2.19 points from the 4. So either 2 above or 2 below the 4. We've talked about correlation several times before, so we're going to move on to talk about the relationship between two variables. Now, correlations, as we've talked about before, are useful when we have 2 scores per individual. So each individual has a score on each variable. Scatter plots are really important in interpreting correlations, so we're going to go through how to draw a scatter plot. And those slides, and there's many slides in the PowerPoint presentation that kind of walk you through each step. So correlations in general can tell you 2 pieces of information. They can tell you about the magnitude and direction of the relationship between 2 variables. The magnitude tells you how well the data correspond to a straight line, so how perfect is the relationship. And then the direction of the correlation tell you whether the relationship is positive, shown by an upward trend, or negative, shown by a downward trend. Okay, so the other slide showed you how to draw a correlation, or excuse me, draw a scatter plot. So this is the kind of thing that you're going to end up with. This scatter plot right here indicates a positive relationship. We know that it's a positive relationship because as one variable increases, for example, as x increases, then scores on y also increase. So this person right here has a low score on x. They also have a low score on y. This person up here has a high score on x. They also have a high score on y. So this tells us about the direction of the correlation. We know that that one's a positive correlation, but it's important to note that this is not a perfect correlation. So what this means, the magnitude tells us, again, how close it is to a straight line. And the fact that it's not perfect, or that it's not a correlation of 1, tells us that there are some exceptions. So for example, we can compare 2 points and say this person right here scored pretty high on x, but average on y. This person scored lower on x, but they actually got higher on y. In general, what we'd expect is the higher you got on x, the higher you got on y. So because this isn't a straight line, means it's not a perfect correlation. This is probably a correlation of 0.9 or something along those lines, because it's not perfect. Now, graph B shows a 0 relationship, meaning there is no correlation. What you can see is when you look at the data points, there's no clear way to draw a line straight through the data points, which indicates that there's probably not a relationship between the variables. Your scores on X don't really predict your scores on Y. This would be a correlation of 0. And then finally, this one shows a negative relationship. Remember, with a negative relationship, a high score on X means a lower score on Y. And likewise, a higher score on Y means a lower score on X. And again, this one's not perfect. It's probably about a 0.85 because we have exceptions to the rule because it's not a perfect. So this is a nice recent example of a correlational study that's looking at the correlations between chocolate consumption and the number of Nobel Prizes a country has won, and each country indicates a point. What you can see is that there's a positive correlation. Countries that score lower on chocolate consumption are likely to be those that have fewer Nobel laureates. Countries that consume more chocolate are likely to be the countries that are also more likely to win Nobel Prizes. This is the correlation of 0.79, meaning that it's positive, but it's not perfect. You can see there are a few examples. For example, if we compare Germany to Sweden, you can see that Germany eats more chocolate than Sweden does. However, Germany wins fewer Nobel Prizes. But there are many countries where this trend is generally true. Now, this is also useful for talking about what we can and cannot conclude from correlations. So what we cannot conclude is that chocolate causes countries to win Nobel Prizes. This is a correlation. All they've done is measured how much chocolate a country consumes and measured the number of Nobel Prizes. They do not know which causes which. They did not manipulate any variables, and so we can't really make any causal statements. There's a couple of possibilities that could be going on here. One is that chocolate influences Nobel Prizes. Maybe chocolate improves cognitive functioning and makes citizens more likely to win Nobel Prizes. However, it could go the other way. Maybe countries that win Nobel Prizes celebrate and therefore are more likely to consume chocolate. So it could be chocolate causes Nobel Prizes or Nobel Prizes cause chocolate. A third possibility is that there could actually be something else that's causing both of these things. For example, maybe a country's wealth or income predicts how much chocolate their citizens consume and also predicts funding for research and how likely they are to win Nobel Prizes. So, because there are so many possible explanations for correlations, it's really important that you do not make causal statements based on a correlation. It looks like there is a relationship between the two, but we do not know which. Moving on to experimental data, we talked about measuring effect sizes in chapter 6. And remember, we were talking about when we are doing an experiment, we want to know if the independent variable had an effect on the dependent variable and how big of an effect it was. And so we call this Cohen's d, or it's also called the effect size. So the way we calculate Cohen's d is we look at the difference between the means for each level of the independent variable. So that's mean 1 minus mean 2. What is the difference between the two groups? And divide by the standard deviation. Because we're dividing by standard deviation, we're standardizing so we can compare across studies. And remember, we have these guidelines all set up to determine how big of an effect the independent variable had on the dependent variable. Okay, in terms of confirming what the data reveal for experimental data, we're trying to confirm whether or not the groups are different. We've talked about confidence intervals before. We're going to take that a little bit farther. So remember that when we're talking about a confidence interval, when we're talking about any statistics, but particularly with a confidence interval, we have to remember that what we're doing in research is we're taking a sample and trying to estimate a population. So we're taking a sample of participants. We assume that they estimate the population mean, but they're not necessarily going to be a perfect estimate. So what the confidence interval does is it gives us a range of scores around which we think the population lies, or it says we think the population score is somewhere between X and Y. Confidence intervals are also sometimes called the margin of error, so you might see this a lot in news reports. So for example, in election polls, last November, they might say things like, well, Obama was leading Romney 47 points to 45 points, but there's a 4-point margin of error. What that means is in their sample, they found that Obama, 47% said they'd vote for Obama and 45% said they'd vote for Romney. But they think that there's a possibility that the true population mean could be 4 points higher or lower than their sample mean. So there's two types of confidence intervals we're going to talk about. First, we're going to talk about the confidence interval around an estimate of one mean. So we're saying, here's the mean we got for the sample. What is the range for the population mean? So in general, this is our formula right here. Remember, because we're calculating an interval, we need to calculate the higher number and the lower number. So for the 95% confidence interval, you can calculate different ones. We're going to focus on 95%. What this 95% means is we're going to say we're pretty sure that 95% of the time the population mean actually lies within this range. So to calculate the upper limit, we're going to take the mean of our sample plus this number t equals t for 0.05. I'll show you how to find t in just a second. But this is just a number that you need to look up in a table and insert in. Now the 0.05 is not something you need to calculate. The 0.05 is telling you that the 0.05 is associated with the 95% confidence interval. So you don't need to calculate that. That's all part of the t number that you're going to put in. So the mean plus t times the standard error of the mean, which I'm going to show you how to calculate. So this is kind of the basic formula. That's for the upper limit. For the lower limit, you're going to take the mean minus the t-value times the standard error of the mean. In order to look up the t-statistic, and this is, again, not something you need to calculate, you just need to plug in the number. You're going to go to the table on page 444 from Appendix 2 in your book. And this is what the table. Now, in order to find the t-value, you need to know your alpha level, which is going to be 0.05, unless I tell you otherwise. This is for the 95% confidence interval. This is the subscript on the t in the formula. You're pretty much always going to be using this 0.05 column. So go to the alpha equals 0.05 column. The other piece of information that you need is to know the degrees of freedom, or DF. You don't need to really understand what the degrees of freedom are. In general, they're calculated by n minus 1, so the number of people in the study minus 1. That's the way you calculate the degrees of freedom. So what you're going to do in order to find the t, you need to know the degrees of freedom. Often I will give them to you. If not, they're n minus 1. Know the alpha level, which will always be 0.05, and find where they meet. So in this case, we've got a degrees of freedom of 15 at alpha equals 0.05. Go to the table, go to the spot where those two intersect, and my t-value is 2.13. It's as simple as that. You plug in 2.13 anywhere in the formula that says t.05, and that's all you need. It is also possible that the degrees of freedom that you calculate might not specifically be listed in this table because this is a summary table. So for example, if you were trying to look up a t with 50 degrees of freedom, what you need to do basically in this situation is estimate. So 50 is somewhere between 40 and 60 degrees of freedom. We can go and look, and you see that the difference is only 0.02. And if we were looking up 50 degrees of freedom here, we'd say, okay, 40 is 2.02, 60 is 2.00. Probably 50 degrees of freedom is going to be about 2.01. So if the exact number is not in your table, it's okay to estimate it. The second piece of information you need in order to calculate the confidence interval around one mean is the standard error of the mean. So again, remember that when we're looking at confidence intervals, we're using a sample mean to try to estimate the population mean. What the standard error of the mean tells us is basically it's an estimate of how well the sample mean estimates the population mean. You don't really need to understand the standard error of the mean. All you really need to do is know how to calculate it. You'll just need to calculate it and plug it into the formula. I'll give you this. SD is the standard deviation for the sample, which I'll give you, divided by the square root of n. Again, n is the number of people in the study. So you'll just need to be able to calculate the standard error of the mean and plug it into your confidence interval. Okay, so we've talked about the confidence interval around one mean. When we're comparing two means, what we're going to do is replace a single mean with the differences between the two means. Essentially what we're doing is we're looking at the confidence interval around each sample mean. So we have a sample mean. We're saying, okay, here's where we think the numbers between which we think the population mean lies. does this overlap with our other sample mean? If they don't overlap, then we think the populations are probably really different. There's a true difference. That would also mean that the independent variable had a true effect on the dependent variable. If they overlap, then it's possible that in the population there really is no difference. So essentially, for the differences between the two means, we're putting confidence intervals around two means and seeing whether those two confidence intervals overlap. Statistically, though, what we're actually calculating is a confidence interval around the differences between the two means. Okay, so again, with the confidence interval around two means, we want to know, is there a difference? Let's hypothetically say that we have two samples. Group 1 has a mean of 57, group 2 has a mean of 49, and we can calculate the difference between the two groups. What we want to know, is there really, would we see a difference in the population? So right now, the difference between the samples is 8 points. But we know our populations might not be exactly the same as the sample, so we have to figure out where do we think the true population mean is and see if so what we're going to be doing is putting a confidence interval around each sample. So for group 1, 57, we say, okay, our sample mean was 57. We think that the population is somewhere between 54 and 60. For group 2, our sample mean was 49. We think the population is somewhere between 45 and 53. And now we want to say, okay, we've got the range where our sample, where our population mean lies. What is the true difference? What are the range of possible differences between our groups? At the very smallest, it's possible that there's as little as a 1 point difference. So at group 1 is still higher than group 2. At the biggest, it's possible that there's as much as a 15-point difference if group 2's mean were 45 and group 1's mean were 60. So we would say that the range around the true differences between the population means is somewhere between 1 and 15. Because this confidence interval does not include 0, we're saying at the very smallest, group 1 is still 1 point higher than group 2, and at the biggest, it's 15 points higher than group 2. Because this does not include 0, we say there really is a difference between them. Just to give you another example, so let's say our means are 53 and 57. So here we have a difference between our sample means of 4. We can again put a confidence interval around our sample means, but for group 2, we think that the population mean for group 2 is somewhere between 49 and 57. For group 1, we think it's somewhere between 54 and 60. And again, here we're interested in the populations, is there really a true difference between the Now, here we have a little bit of a different situation because there is an overlap between our two confidence intervals. At the biggest end, it's possible that there's a difference of 11 points, that group 1 is 11 points higher than group 2. However, on the smallest end, the smallest possible difference is actually a negative number. It's a -3. What this means is that group 1 is actually lower than group 2. It's the opposite of what we found in our sample. So our confidence interval is -3 to 11. Because the confidence interval for the difference between the two means overlaps and includes 0, it means that we conclude that there is no true difference between the groups. So I showed you kind of visually what we're doing. Numerically, what we're doing, again, is we're finding the confidence interval around the difference between the two means. Essentially, we're using the same formula as the confidence interval around one mean. We're substituting it with a couple of things. So here's our formula. Remember, around one mean, we just had the one mean. Here we want to know about the difference between the two means. So instead of just having one mean, we're going to take the difference, mean 1 minus mean 2. Here I've got it all in one formula, but basically for the upper limit, you'll add. For the lower limit, you'll subtract. Our t-value, we're going to look up the exact same way. And then instead of the standard error of the means, here for the difference between the two means, you need the standard error of the difference between the two means. There's a complicated formula in your book. You don't need to know it. For the standard error of the difference between the two means, I will give it to you, and you won't need to calculate it. So just like the confidence interval around one mean, for the confidence interval around the difference between the two means, all you need to do is plug in the numbers. And again, remember, you want to know, does it include 0? If one number is negative, if your upper limit is positive and your lower limit is negative, as long as one of those two numbers is negative and the other one is positive, that means that your confidence interval around the difference between the two means includes 0, which means there's a possibility that there really is no difference between the means, which means we can say that there is no difference. If your confidence interval does not include 0, then we consistently say that we're very sure that there is a significant difference between the two groups.